Hello, folks. Welcome to Rational Science. Another day, another bit of science. And we're going to be talking about spaghettification today. Spaghettis. You like spaghettis? Well, not if you're turned into one by a black hole. I don't think you would like it. But that's what we're going to talk about today. But let's get on with first with the extinction segment, a couple issues there, and then we're going to answer some questions, comments that people made since last time. Okay, so let's go with this extinction issue here. And let me just show this first. There's two mechanisms we propose for extinction. One is the overturning of the demographic pyramid. The other one is overturning of the ecological pyramid. Okay, and the one on the right, the ecological pyramid, has to do with mass extinctions, whereas the one on the left, the green one there, has to do with background extinctions, which we call the disappearance of one species. Okay, mass extinction is, on the other hand, a disappearance of a food chain. Okay, so that's the difference between them. And why do I bring this up? Well, someone made a comment, and he said the following. He said, those species die because their gene pool is exhausted. Genetic exhaustion, you could say, right? Well, yes and no, it's not complete. Yeah, that is one of the elements, okay? We have two issues here. The first one is that there's an overturning of the demographic pyramid. Okay, that means that you see there on the right what happens usually with humans, that the population pyramid overturns. We become older and we have fewer children. Okay, and so if this process continues, well, just take it into the future and you'll find out what happens. What happens is that we produce fewer and fewer children and we have more and more old people. At some point, there's a critical point where the old people have to go and the young people are not there to replace the population. That's what it happens. That's happened to us already, and there's no way to overturn a population pyramid once it starts. And ours started in 1963. Okay, that's when we had the last highest level of reproduction on Earth, growth rate. It was at 2.3. Today it's around 1.0, and they figure out that if everything goes as it's going now, by mid-century we're going to have zero population growth, known as ZPG, meaning the population pyramid of humans has pretty much completely overturned by then. And that means we will be producing fewer and fewer children, and more and more older people will be dying, and so the population will go in negative growth across the planet as a whole. Some countries will produce more children, others less, but in general, the population on Earth will be decreasing on its own. We need to do nothing about it. Okay, and the other issue for this fellow, one is the genetic diversity, and this is how I illustrated in my book there, in the Neanderthal book. We say that when a species migrates out of the main branch, main trunk, you could say, and this is just a branch that moves out to a different region and kind of becomes isolated from the trunk, well, they meet other factors like diseases, climates, predators and prey, foods, etc. And at the beginning, this new species that is created diversifies quite a bit. In other words, they're getting bombarded by new factors around them, environmental factors. And because of that, the genetic diversity increases pretty much, I would say, rapidly. But then at some point, when they become settled, they migrate and they don't interbreed with any other species. What happens is their genetic diversity steadily declines. Okay, and especially when they get to the last stage, which is sedentism, when they do not migrate anymore. What happens at that point in time, or starting at that point in time, is the genetic diversity essentially is shot. It just there's new material entering the gene pool, other than the daily mutations, but they're overcome usually by population bottlenecks and founders effects. So that's essentially the curve that I say happens to all species, whether plant or animal. I call it the law of genetic diversity, but it's not a law. It's just that's the way Mother Nature runs her shop. Okay, so yeah, it's not a law. It's just people like the word law, and so I put it there. No, it's not a law. Okay, not Bill's law. Okay, or whatever. So there's two components. One is the overturning of the population pyramid, and the other one is the genetic diversity, and that happens to all species, no matter what. No species lives millions and millions of years. Okay, they think they do, but they don't. If you take maybe the lungfish of today and you compare them with the lungfish of maybe what is it, Carboniferous or Devonian or whenever they came around. One would think of the other one as a Neanderthal. Say, hey, you're very different. I'm not going to have sex with you. You know, there's no reproductive sex between such species. So that entity over there is a different one than the one over here. You know, so they're not the same. You would have to have continued breeding forever in order to achieve that. And when you do that, what you get is two things: the overturning of the population pyramid of that species and the loss of genetic diversity. Those two trends are inevitable in the long run for any species of plants or animals. Okay, and then another fellow, well, not another fellow, this came out of an article. It says scientists identify 7 star systems that may be hosting alien megastructures. And what are they talking about? Well, they're talking about all these science fiction, which they call science, where civilizations evolve. They become super intelligent, I guess. That's the way they see it. And by that they mean that they manage to acquire technology and knowledge and intelligence and whatever to be able to not only travel to the stars, but somehow harness the energy of all these stars and maybe create some galactic civilization. The whole galaxy belongs to them. They're owners of it all. And what they do is use the energy of the stars to power whatever they have to power. And they have these dreams of how these aliens, essentially manage to conquer first the star system, maybe a solar system, then a couple solar systems, eventually the entire galaxy. And this is nonsense. This is poppycock. It has no place in science, but these people think they're scientists and they study all these things. And there's one group that, in fact, that where this came from, really, and it's a futuristic group. They're called Project Hephaestus. And what they do is they study, all these, or they look for, not that they study, but they search the skies for this dream where they want to see some kind of galaxy out there that, or maybe a star system, a group of stars where some civilization out there has managed to, conquer it and harness the energy and live off of the stars, etc. And they look for it out there. That they spend their valuable time looking for all this nonsense. Okay? And they're trying to find out whether they can see some aliens out there moving around, maybe, or not the aliens themselves. The telescopes may not be able to search to such degree, but they want to see the big structure. And they're going to interpret whatever structure they see out there, some light, some fancy light, and they're going to, there's a civilization that has developed to the point where they conquered all these stars and they're thriving with all their energy that they steal from the stars, and they live happily ever after. Another group that does this, aside from the Hephaestus, is the famous SETI, Search for Extraterrestrial Intelligence. And you had all these people who study the skies that look for some kind of intelligence out there, maybe a signal, maybe a noise that comes down to us, and they're going to try to interpret it as, oh, this has to do with some civilization out there that sent us a message. And of course, they hire very high-priced people like Morgan Freeman to represent them, to see if they can get more funds to search the skies for this nonsense. And so why is it nonsense? Why is it poppycock what these people are doing? Well, because we have no chance whatsoever of seeing another civilization in whatever little time we have left here on Earth as human beings, as mammals, right? The mammals are undergoing the sixth mass extinction, and we will be gone, I'd say, quite soon, geologically speaking. In fact, I think those people living today, are part of the last generation of humans on Earth. There will not be great-grandsons or any of those things come in the future. Okay, so what's the story? The story is that, we barely can get to Mars, and here we are as advanced as we can possibly be. Technologically, we've mastered electricity, magnetism. Not that we know what they are, but we mastered the technology that are based on electricity and magnetism. We violated gravity. We can leave the planet, with our rockets, etc. And we haven't even gotten to Mars. We probably got to the moon. I think we did, but I don't think we're going to get to Mars. Maybe we might. We're that iffy there. We might make it, we may not. But for sure, we're not going to settle Mars. We're not going to colonize Mars. There's no purpose to do so. Okay, we're not going to terraform Mars. None of that will happen. The best we can do is just get to Mars and say, hey, we made it, plant whatever flag we plant out there and then come back. That's about it. And I doubt that even that might happen. But it could. And so this notion that intelligence grows exponentially over time, what they call the singularity, where after you hit that point in technology, everything just multiplies exponentially because the robots do, or the AIs do the thinking for us, and they can do a lot better thinking than humans and so on. Well, all that is poppycock. All that is science fiction. It's not even science fiction. I think it's just fantasy, which is, I think, a higher degree than science fiction. We cannot even leave our solar system. And that's happened to any other civilization that ever lived in the universe, just like us. In other words, if there were humans out there, human-like people, creatures or whatever, they reached as far as we did, and then they became extinct. That's how it is. That's how Mother Nature planned it. There's no chance of living forever, millions of years, and being able to do the things these people think, that they're just going to colonize the... Not sure if I'm still there. I hope I'm connected again. I was disconnected momentarily. I don't know why. Okay, let me continue. I hope I'm still on. Can someone please confirm that you can still see me? I received a message from YouTube that I was disconnected. Okay, thank you. Anyways, the issue is that, if there's another civilization out there with at least as much technology as we have, okay, today on Earth, they're very far away in the question, issue of distance, right? A question of distance. But more than that, there's an issue of time. They certainly will not develop at the same time that we did. In other words, they're not going to reach our level of technology at the same time that we did. They probably already did hundreds of years ago, more likely millions of years ago, and likely have not yet developed it. In other words, again, millions of years in the future. So it's more a question of time than it is one of space. But space also, we look around in the region where we live, in our neighborhood, and we can't find any signs of life. And so life is very scarce out there in the universe. You can tell that just in our solar system. We're the only planet with life. okay? And so that's just in our neighborhood, real small neighborhood. If you go out there and you look through the stars in the neighborhood, same thing. You'll find very little signs of life. You know, they can speculate and say, oh, this plant might have water, this plant might have oxygen, etc. But to see a civilization in one of those planets, one of those few planets that might have water and oxygen, and have it at the same time as us, the same level of development, it's next to impossible. So it'll never happen, not in what little time we have left. And so all these people like SETI and Hephaestus, they're just wasting their time. That's my 5 cents worth, okay? Okay, let's move on to some of the questions people made since last time. Here's comments that people made. Here's one fella, and he says the following. He says, is light generated by the friction of the ropes? And it's not really the friction of the ropes. What you have there really is torsion. You have the in situ torsion, and gives a little bump to each atom, the ones that are at each end of the rope. So both atoms receive constantly and simultaneously, you know, this little thump, this little torsion there where the threads fork out, and one becomes the electron shell and the other one becomes part of the proton dandelion, as we call it, okay? So the threads make up the atoms, and the atoms, on the other side, you have the threads come out again and turn into a rope. And so the whole universe, all the atoms in the universe are physically connected. And what you have is they're doing their quantum jump, they're pumping back and forth what Niels Bohr thought was a little bead going back and forth between energy levels or orbitals. That's not what happens, because you would have to explain, why doesn't the bead fall completely, negative bead, right, fall completely into the positive proton, or why doesn't it spontaneously fly away? Why does it jump between energy levels? Why can we find it there? You know, and this explains it, because it's really a membrane, not a little bead. It's a membrane that's pumping back and forth at great speeds, vibrating, moving around, and while it does so, it torques the rope. So it's not, it's torsion, it's not friction, okay? Is there a tiny friction when the rope torques? I don't know, I think not. I would venture to say not. It's like if you have a rope, you torque it, I'm not sure there's any friction between the two threads, which is, I think, what he was referring to, okay? Okay, here's another fellow. He says, the following says, Bill, is the rope for light the same rope for gravity? Does gravity move at the speed of light? I'll answer the second question first. Now, gravity is instantaneous, you could say, which is the wrong word to use, because instantaneous, there's no such thing as instantaneous. We either have one frame of the universal movie, or we have two. And we have two, which is what motion is about, two frames, right? Two locations of every atom in the universe. You can call it that motion cannot be instantaneous, because instantaneous really refers to what's in a single frame. So we cannot say that gravity or anything is instantaneous. There cannot be. There's a contradiction in that term. We need to understand what we mean by instantaneous. And people think of that being motion that happens in a single frame. That cannot be possible. Mona Lisa needs two frames in order to smile, okay? Because smile is a verb, and verbs require two frames of the universal movie as a minimum, okay? And so we just say that gravity acts instantaneously. Why? Because it's location specific. Weight is location specific. You're out there, you have an astronaut out there in the middle of space, right? And he's got a certain weight at a certain distance from the Earth. Let's say 100 miles, right? He's 100 miles from the Earth, from the center of the Earth, or more, let's just say 1,000,000 miles from the center of the Earth, right? So he's very far away. All he has to do is move an inch, a millimeter forward, his weight already changes. Instantaneously in that sense that once he changes location, his weight changes, gravity changes for that asteroid. Okay, in that sense, it's instantaneous. Location is instantaneous in the sense that once you move to another location, it's instantaneous once you're there. Okay, and that affects gravity instantaneously in the sense that gravity will change immediately as soon as you change your location. Okay, that's what we mean by instantaneous. But there is, instantaneous again is an irrational term. There is no such thing as instantaneous because it means that there's zero time and something happened. And there is time involved or motion. There's a change in gravity as soon as you move a millimeter or even a micrometer. Okay, your weight already changed with respect to the object where you're measuring this, right? But now let's go with the first issue. Is the rope for light the same rope for gravity? And the answer is yes, but here we have to put it in the right context. Here it is. The rope is really the gut in grand unified theory and the toe, the theory of everything that mathematicians have been looking for years. What do we mean by this? Well, if you're going to talk about gravity, we're saying, look, the gravity is mediated by all these ropes that connect every atom of, in this case, the example is a box, to every atom on Earth. Okay, we didn't draw them all, just in case. So we have all these electromagnetic ropes binding one atom to every atom on Earth and vice versa. One atom on the Earth bound to every atom of the box. So it's in both directions. And of course, I did not draw them all. So what is that rope that interconnects every two atoms? Well, there you see it on the upper right. Okay, you have the 2D and the 3D version. They're pumping, doing their quantum jump, and what they're doing is torquing the rope. What goes along the rope, what propagates in both directions, is light. And at the same time, as the box moves closer to the Earth, and when there we have the example of the astronaut falling to Earth, as the astronaut gets closer to the Earth, the ropes fan out. So with the rope, we are able to do two mechanisms. Along the rope, any single rope, we have light. We have the torsion known as light. And all the ropes produce this effect we call gravity, which is as the astronaut gets closer and closer to the center of the Earth, the ropes fan out, and that is a measure of the acceleration of gravity. That's what we call acceleration of gravity. And as you can see, it's a function of distance, just like Newton's equation tells us. Okay, so that's the context. So we have to put it in the proper context when we say, well, is the ropes the same thing as light? Is light the same thing as a rope? They are. In other words, the rope is the mediator, the physical mediator. Okay, but light is a torsion along each rope, whereas gravity is the all these ropes fanning out. The closer, we'll call it the acceleration of gravity, is as the object approaches the Earth closer and closer. An asteroid could be an astronaut, whatever. As it approaches the Earth, the ropes fan out because every atom of that thing is bound to every atom that comprises the Earth. Okay, so those are the two mechanisms, one for light, one for gravity. We call it the grand unified theory or theory of everything because we need look no further. And here's an article that came out this week that kind of puts it also in the right perspective. Here you'll see it. Scientists shrunk the gap between atoms to an astounding 50 nanometers. What are they saying? Well, they're saying here, it says, after cooling the system to near absolute zero, right? Squeezing two dysprosium atoms only 50 nanometers apart, the atoms displayed exotic quantum states. And what are these? Well, they are including magnetic interactions 1,000 times stronger than if the atoms were the typical 500 nanometers apart. So what are they saying? They got these two atoms closer together, right? They were able to do it at cold temperatures, etc., etc. We don't care the conditions. We care about the explanation. It says one of these behaviors is an effect caused by an enhanced magnetic state where the two dysprosium atoms a long distance connection with each other. Did I hear connection? Long distance, what? Connection with each other. They're connected, right? Transferred heat between layers separated by what? By a vacuum. Well, we have a contradiction with these fellows, and again, it's because these people don't understand their contradictions. On the one hand, they talk about connection, which is a physical term, saying something is connected to something else. Hopefully it's connected by a physical object, and these people say it's separated by vacuum. Well, we got a contradiction. Either there's a physical object we cannot see or touch between the two atoms, or we have absolute vacuum, there's nothing between the two atoms. Which one is it? Okay? And then continue. Another side effect was collective oscillation, where the vibration of one layer caused the other layer to vibrate simultaneously. When the atoms separated from each other, both of these effects dissipated, right? So when they separate them, they don't have that fuzzy little magnetic or field or whatever you want to call it, acting between the two atoms. Until now, heat between atoms could only be exchanged when they were in the same physical space and could collide. Now we have seen atomic layers separated by vacuum. Again, are we separated by vacuum, or is there a physical object that we cannot see or touch? And they exchange heat via fluctuating magnetic fields. No, they can't do it via magnetic fields, because magnetic field is not is a concept. It's not a physical object. You have to identify the object in physics. Otherwise, you cannot give a physical interpretation. And so what's the issue? The issue is that these people are really developing technology. And they call developing technology, they call that science. That's where the problem is. No, science has nothing to do with technology. Absolutely nothing. Science is about explaining. Technology is about developing gadgets, okay? And they're two different, you can say, disciplines or activities. One has nothing to do with the other. Now, if you can develop technology because you have this insight, extra insight from science, more power to you. I'm just saying these two things are separate. Technology is one thing and science is another. What these people cannot do is explain. They are not scientists, they are technologists, they are mathematicians who want to do technology or develop technology for computing or for whatever. None of that has anything to do with physics or with science. Science, you need to explain. You need to tell me how it works, what the mechanism is. If you can't, you're not a scientist. That's how simple it is. And for that, we need to define what science is. Nobody has done so in the last 400 years, since the so-called scientific revolution. Okay, here another fellow says, fields, forces, energies are physical. Well, for that, you need to define what physical is. Physical, that which has shape. That's what physical means, okay? And field is a bunch of numbers, so that's not anything that has shape. Force, there's push or pull, two verbs. That doesn't have shape. Verbs don't have shape. And energy is defined as the capacity, blah, 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 blah. And the capacity is not a physical object. Okay? So none of these qualify as physical. Very straightforward, very simple. Okay? Hopefully anyone can understand that. Okay, here we have another fellow. He says the following. Since atoms attract each other due to magnetic influencing dipole induction, it's an electric phenomenon. Okay, so why should macroscopic attraction of the Earth be any different? Atoms are magnets because magnets are made from atoms. Well, I don't know what monastery this fellow studied in. All he's got to do is tell us, he says electricity or magnetism or whatever fields pull two atoms together. Well, we want him to give us a mechanism of how any of those does it. How does electricity pull those two atoms together? How does magnetism pull those two atoms together? That's all he's got to do. Show us. You know, illustrate a mechanism. Show us how that atom, which is the atom they're using, if you got a different atom, more power to you, okay? Because that is an irrational atom. But that is the atom that is taught in schools all over the planet. It's the Bohr atom, Bohr-Rutherford atom. We have the Rutherford's proton and Bohr's electron there, little bead jumping back and forth. That's the atom. And all you got to do is show us the mechanism of how one atom attracts another. So once you can do that, you can show us how magnetism or electricity or whatever you believe in, how it works, how it acts to get two atoms together. Only then can you talk about, saying, okay, how does the sun attract the earth? Is it through electricity, through magnetism? First do two atoms, then we'll extrapolate that to, bigger stuff like planets and other celestial objects. Okay, so here we have another fun. He says the following. He says, in lead dioxide, PbOH, O2, which is used as the active material to the positive plate of the battery. The lead atom is in the +4 oxidation state. This is because each oxygen atom has an oxidation state of -2. So balance the charges in the molecule. The lead atom must have an oxidation rate of +4. Yeah, what he's saying is that a lot of this is just math, okay? And with this math, they are able to describe, not explain really, but describe what is happening during a reaction. In fact, this is just one reaction. You can apply this to any chemical reaction. Essentially, you have to balance what's on the left with what's on the right, okay, on the other side of the green arrow there. Okay, but it's important to note that this doesn't mean that the lead atom is short of 4 electrons. Rather, it means that in the context of the molecule, the lead atom has effectively lost 4 electrons to the oxygen atoms. That's interesting because he says it doesn't mean the lead atom is short of 4 electrons, but then he says 4 electrons are donated or go to the oxygen atoms. And again, this is why all these people do a lot of math, but they have no explanation. They cannot illustrate what they're talking about, because if the electrons move, if they are lost to the oxygen atoms, then I don't know how he can say, on the other hand, that doesn't mean that the lead atom is short 4 electrons. What do you mean they're not? He just donated them. So again, they have all these contradictions because they cannot illustrate what they're talking about. They cannot tell you what the mechanism is. That's the issue. In the context of the lead acid battery, the OH group does not exist freely, but is part of the water H2O and sulfuric acid H2SO4 molecules. During the battery's operation, these molecules participate in various reactions, but the OH group itself does not carry a charge of -4. Yeah, and again, the problem that this fellow has is that he's wanting to talk about the chemical math, the mathematics of a chemical reaction. That's what he's talking about. And the video that I put up this week on this refers really to something else. We're not doing math, we're doing physics. The math we just took from quantum mechanics, and again, it's what's on one side of the green arrow, and you equate it to what's on the other side, and they better match. The numbers have to match. But that doesn't mean that math represents what's happening in the real world as far as the physics of it. What's happening qualitatively? What physical interpretation do we give to this? That's the issue. And what we're saying essentially in that video is, because that's going to lead to the following video, is that somehow the chemical reaction compels the lead, okay, on the right to turn, I think we had that going clockwise, okay? Or if it's counterclockwise, no problem. But it's taken all the way all around to the other side where you have different chemicals there. And what it does is, hopefully if it's clockwise over here, it's counterclockwise at the other end, and vice versa. Okay, if you just take a rope and you have it in a curve pointing towards you, if you turn this one counterclockwise, eventually that counterclockwise will turn into clockwise on your other hand. Okay, and vice versa. If you turn it clockwise, that'll go all around, and you'll see that on your left hand, you're going to have it counterclockwise. So all we're talking about is that there's going to be a chemical reaction in the H2SO4, and what it does is compel the atoms that form the wire or whatever you have there, hopefully it's some kind of lead wire, to move in the counterclockwise direction, and then comes out the other end as clockwise. This positive and negative that quantum talks about, Mother Nature doesn't understand what positive and negative are. She does understand clockwise and counterclockwise. That is physics. Plus and minus, positive, negative, north, south, that's all garbage coming from math. Mother Nature never went to school. She doesn't understand math, especially human math, okay? And again, this is all this fellow has to do. He's got to tell us what the atom looks like before he can talk about, losing electrons and gaining electrons and all that kind of stuff that he talked about just now. No, you got to tell me, what your atom looks like to begin with before you tell me how it lost an electron. And right now, this atom that you see there is an irrational atom. It's a Bohr-Rutherford atom, and they have this little bead, negative bead, that somehow, falls and rises from to and from energy levels and orbitals, whatever. And what we're talking about is, why does that electron bead remain faithful to the proton center? Okay, that's the only issue we've got to answer. And there is no answer to that. To this day, after 100 years of so-called quantum mechanics, we still don't have an answer to this question, which was, by the way, incidentally, the question that led us to investigate the electron. Why doesn't it fall to the nucleus? And here we are 100 years later, and we have an answer to this question. Mathematical physicists, mathematicians, they have not been able to answer this question. Why doesn't the electron bead, negative electron bead, why doesn't it get attracted to the positive proton if positive attracts negative? And they can't answer that question. And the answer is simple. Orbitals are not orbitals. What they are is a membrane. What we have, the electron is a membrane, and that encapsulates the proton star. Okay, so we have a different model of the atom. We can explain it, but the mathematicians who rely on the Niels Bohr, Ernst Rutherford model, they cannot answer, and they never will, because it's the wrong model. It's an irrational model. Not wrong, it's an irrational one, because you cannot justify it. That's the whole issue. And final question that a fellow asked there says, it may pain you to know that Einstein also came to understand the necessity of an ether. I believe that is what he's referring to in the letter about fields. Okay, and Einstein wrote a book on the ether as it relates to relativity theory. There you see it. And the Einstein ether theory is a modified theory of gravity that breaks Lorentz symmetry by introducing a dynamical vector field called the ether. And Einstein in 1920 gave a talk over there at the University of Leiden. And he says the following: said, we may say that according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. Okay? According to the general theory of relativity, space without ether is unthinkable. Okay? So was Einstein an etherist? Well, he was. Remember, in the 19th century, they still hadn't gotten rid of the ether. And so Einstein was born in 1879. So he was an etherist by education, And so these people were still talking about the ether. That was kind of displaced or replaced, you could say, by space-time on the one hand, and the false vacuum that quantum mechanics has today, this so-called vacuum. Both of them, both space-time and false vacuum, anything coming out of mathematical physics is ether. These are all ether theories, because ether simply means bunch of particles, and they serve as a background. Some of them think of them as a sandbox. All the things are fixed, the grains are fixed. They're just sitting there. And others think of it as like an ocean or as air, that these particles are moving around. So there's these different notions of the ether, but they're all particles. Mathematical physics, since the days of the Greeks, has always been particles. That's the background, particles. And that's what the ether has been, and that's what it still is today. They talk about particles coming from space. What do you mean particles of space? Are you saying first of all, are they round? If they're round, what's in the interstices? So you have to tell me what separates one particle from the other. That's the first issue. The other one is, you have all these particles, so when they come in, whether it leaves a hole behind in space, a hole in space, a hole in nothing. If not, what is space? Is space made of all these particles? If it is, when you pull one into the real world, virtual particle for a split second, did it leave a hole behind? So there's lots of questions there. And what you end up eventually believing or understanding is that not only is quantum and ether theory, yeah, it is, but they haven't solved the problem. They haven't solved what is space. That's the issue. And either space is made of particles, or particles are occupying space, which means you still haven't told us what space is. And you can't say empty space because space is empty. It's like saying empty, empty, or space, space. You're saying the same word twice, you know. So, yeah, you need to define what space is. And none of these people have ever done so. That's the issue. Okay, so let's get into the subject matter today, the main subject, the main course, and that's going to be spaghettification, okay? And that looks more or less like this. Here's illustrated. You have this astronaut. He's flying to the center of the black hole, all the way down to, should be a ball. Here's a 2D version, kind of, you know, it's the disk version. But you have to think of it as more like a sphere. And the astronaut's going to go all the way to the center of that sphere, you know, going to ride the whole radius all the way down to the center. And the question is, you know, what happens to him? And they say, you know, this spaghettification is that the guy is stuck somehow or very close. His head is very close to the event horizon, which is the shell that you could say, you know, the shell that encapsulates the black hole. And his feet are going to be close to the center, to the singularity, somewhere close. We're going to find out today they never reach the singularity, or sometimes they do, who knows, depending on the mathematician you talk to. So this guy is stretched like you wouldn't believe, you know. And so that's what spaghettification is going to be more or less about. We're going to go into a little more detail now. Okay, but the issue with spaghettification is that it involves time. You can't do spaghettification without time. You need time, absolutely. Okay, and so we need to find out what is time, and it's a very important parameter in mathematical physics, so-called physics. What do we mean by that? Mean that, you know, it's one of those strong parameters. You need time, but you can't use the word time. You can't use the clock. What you need is the seconds, the minutes, the years, the months, whatever. You need the units. That's what you're going to put in an equation. You can't put the word clock into an equation. That's important, okay? So they're not going to talk about clock time dilation, for example. They're going to talk about time dilation. It's time that we dilate, not the clock, right? Okay, so we need a definition for time. What is time? And you know, when in doubt, go to the gurus, especially the people who set mathematical physics in motion. And here we have one of them, and his name is Isaac Newton. And what did Isaac come up with? He said in his Scholium, his great book, right? I do not define time, space, place, and motion as being well known to all. That's how he starts his book. He called himself a scientist. He called himself a physicist. He was neither. A scientist, the first thing he does is define. You have to define. If you don't define, you've surrendered your right to be called a scientist. Okay? So Isaac Newton was not a scientist. He was just a petty mathematician, just doing some numbers there. That's all he did. He did not understand the physics of the universe. In fact, he had no idea what gravity is. Okay? And then he continued, despite saying that he was not going to define it, then he gave it a shot, or kind of gave it a description what time is. It's absolute, true, and mathematical time of itself and from its own nature flows. Time flows. You can't use the word flow to refer to time. You can say duck flows, you know, the water flows, a rock flows, you can, or a tree flows down a river, or something like that. You can say that a thing flows. You cannot say that time, a concept, flows. It's like saying love flows. You know, it's very poetic. You can use that in a poetry, but it makes no sense in physics. You cannot say time flows. But he says, equably, without relation to anything external and by another name, is called duration. Yeah, duration is a synonym of time. Time is duration, duration is time. Great. What have we learned? Just words. We just said A is equal to B, B is equal to A, or X equal to Y equals to X, right? Relative, apparent, and common time is some sensible and external measure of duration by the means of motion. Okay, so he got one aspect right, but he says, which is commonly used instead of true time, such as an hour, day, month, year. In other words, he says, look, it's got something to do with motion. Some people equate motion with time, but he says there's kind of like a difference there. And yeah, since he didn't define motion either, as you can see, time, space, place, or motion, we have no idea what he's talking about. And the funny part is that he's credited with discovering the 3 laws of motion. And those notions had existed already from the days, at least since Galileo. Galileo died the year that Newton was born, so that's interesting. But Galileo already had some of these laws of motion, as they're called. So Newton not only did not define motion, but he did not come up with the notions that we have in the 3 laws of motion. Those notions existed before. The only one you can probably give him credit a little bit for is the second law of motion: force equals mass times acceleration. Other than that, Newton didn't come up with anything. And here we have an issue of space. He says he's not going to define space, but it turns out that Einstein had a different notion of space. So it was incumbent on Isaac there, on Newton, to define space, because he said, oh, we all know what it is. Well, apparently not, because today we have a different notion of space coming from his own religion, from mathematical physics, and it's a different kind of space than he thought about. He thought about an absolute space, and today we have this relative space. So Newton did not do us a favor by not defining key words of physics. And in fact, space is a word of physics, but time is not. We do not have any use for the word time in physics. Time is only a descriptive tool. Math describes, physics explains. We're done. We never need any notion of time at all in physics. It doesn't give us any explanation, and we need explanation. Some people don't even understand the difference between descriptions and explanation, but that's another story for another day. Okay, here we have the definition of time that we have today. After 400 years, you would think, well, someone defined time finally, right? You'd be surprised. And here it is. It says, time, what a clock measures. I like that. That's a great definition. What is weight? Weight is what a scale measures, and what is length? Well, that's what my ruler measures, whatever that is. Love that. What a clock measures. And that's probably the most important definition we have today, the closest one we have. Then you have these other definitions. I pulled them out of different places. The indefinite continued progress of existence and events in the past, present, and future. That's, I think, out of the wiki. And the problem there is past, present, and future can't be used to define time, because time is past, present, and future. So if you look up these words, past, present, and future, you'll find out that they have the word time as part of the definition. And you can't have that, okay? Because otherwise you have circular definitions. Another group expert out there, the ongoing sequence of events. Now, the measured or measurable period, like a period at the end of a sentence, is that kind of period? Period, if you're talking about period, you're already talking about time. So you can't use the word period to define time, but they don't understand that. During which, period during which, obviously you're talking about time already. An action, process, or condition exists or continues, meaning duration. And then you have time, non-spatial continuum, that is measured in terms of events which succeed one another from past through present to future. Again, people have never learned how to define words scientifically. And so what can we conclude? Well, we conclude that we have no definition of time today. In fact, they'll tell you right in your face that they have no definition. Defining time in a manner applicable to all fields without circularity has consistently eluded scholars. There you have it all. There it tells you once and for all time, we have no definition of time today. And continues, says, time in physics is operationally, functionally, operationally, those are all irrational definitions, because it means you run some kind of experiment and then you come up with a definition. The way we do it in science is the opposite. You first define, then you can do whatever experiment you want if you're going to do experiments. Okay? It says operationally defined as what a clock reads. Great. That's great. The operational definition of time does not address what? The fundamental nature of time. Okay, so we have no definition of the word time. Nobody has any idea how to define time out there. And so we had to define it for them. Even though we don't have any use for time, we did define it so that they know what time is once and for all. And then they continue. Wikipedia says, time is often referred to as a fourth dimension along with three spatial dimensions. In other words, they're equating time with these length, width, and height. They're saying these spatial dimensions are no different than time. Okay, that's what they're saying. That's why they talk about four-dimensional what? Space-time. Okay, that means this space-time thingy has four dimensions. Length, width, and height, and the fourth dimension is time. That's what they're telling you in your face. Okay, hopefully everybody understands that. At least what they're saying. Not that you can visualize what they're saying, but certainly you can understand what they're trying to get across to you. They're saying time flows perpendicular to the other three dimensions. We don't notice it because we're not four-dimensional beings. You have to go into the fourth dimension, be a fourth-dimensional being, then you will see the light. And, of course, you'll have to drink a lot of beer to see that, right? Anyway, it says, through advances in both theoretical and experimental investigations of space-time, it has been shown, proof, evidence, experiment, that time can be distorted and dilated. So time is a concept, it's a dimension, but you can distort and twist it and bend it and warp it. Particularly at the edge of black holes. Oh my God, never go over there in the black hole because they're going to warp your time. Yeah, and that's how they're going to get this spaghettification thingy going. They're going to take, something to the edge of the black hole, and then they're going to fool around with time. Okay? That's where we're headed. Okay, so here's proof, evidence that time is a dimension. Again, you can see that this is what they call a space-time diagram, and that's what they do. They put time as a coordinate, dimension, vector, whatever you want to call that. Actually, none of these are any of those. What they are is number lines, which they put arrows on, like if time flowed in a given direction. And when you ask them what direction does time flow, they say forward. It flows forward. Yeah, the only problem with that is your forward is opposite to my forward. So whose forward is time going? My forward's going in that direction, and I hope you're all facing in the same direction I am so that we're all in the same forward direction of time. But if your forward is in my direction, I don't know what forward means. No, forward is not a direction, but that's what they say. They say it's forward. That's the direction of time. And yeah, here we have a guru, expert, right? Mr. Stevie Hawking. I call him Stevie Wonder. That's what he is, and or was. And this is what he tells us about time being a dimension. I want you to listen to him carefully. He says the following: an event is something that happens. Okay, an event is what happens, yes. But he says it happens at a particular point in space and at a particular time. No, that can't be, because particular space and time is a static concept. It's a single frame of the universal movie. That's a point in time, and in just a single point. But if you're going to have time or motion, you're going to need at least two frames, and you cannot have a particular one, a specific one. Okay? And so you can't represent it with a point. You would need a point that stretches to 2 frames of the film, and that's irrational, because a point only occupies, a dot only occupies 1 frame of the film. So we have a contradiction there between point and time and point and motion, right? Point and 2 frames of the movie, of the universal movie. So one can specify it with 4 numbers or coordinates. Yeah, you can do that with as many coordinates as you want. It doesn't matter. There's only 3 coordinates, and that's, longitude, latitude, and altitude. Those are the 3 coordinates. There's no other coordinate. But if you have a 4th one, please let me know, and also tell the bartender to give me whatever he gave you, right? Again, the choice of coordinates is arbitrary. One can say use any three well-defined spatial coordinates and any measure of time. So he says, again, they're indistinguishable, all these coordinates that he's talking about. But he says it better in the last paragraph there. It says, in relativity, right, there is no real distinction between the space and time coordinates. So dimensions, coordinates, whatever you want to call them, there's no difference between the spatial ones and the time one. How can it possibly be? I thought length, width, and height are a little different than, ticking clock. They seem like different to me, right? I don't know about you, but they seem just very differently. And so he says they're the same. And here you can see why, okay? Why he's confused, why Stevie Wonder here is confused. And there it is. Because we have all these definitions, and all of them refer to the same thing. They're referring to number lines. They're not referring to dimensions, coordinates, or vectors. What's a dimension? Minimum number of coordinates. What is a coordinate? It's a number. So dimension comes out to be a minimum number of numbers. That's the definition of dimension. And coordinate is a number. Vector is a quantity, meaning a number with a magnitude. Meaning, again, they're talking about numbers, and they say direction. The problem with direction is that direction belongs to physics, number belongs to math. Never the twain shall meet. One is quantitative, the other one is qualitative. And no vector, math has no use for direction. Direction is not a word that we can put it, it's not in math, you cannot put direction in an equation. I can't do anything with direction. You can't say direction is equal to 4 plus 5. I can't do anything like that. So direction doesn't belong in math, and magnitude, quantity, number don't belong in physics. Okay, so keep them separate. Keep your trash on your side of the math line. Okay, number line, that's what it is. What all these mathematical physicists work with. They work with number lines. And that's why Stevie Wonder there said, there is no difference between a spatial dimension and a time dimension, because he's not talking about dimension. He's not talking about length, width, and height. He's talking about number lines, which is all that they use in the religion of mathematical so-called physics. That's the issue. Okay, and so here you see it illustrated, okay? You see the difference between math and phys, okay? Physics, you have length, width, and height for dimensions, and they're qualitatively only. You have the so-called coordinates, right? And they're longitude, latitude, and altitude. And you have vectors, which are depth, breadth, and elevation. And you can see that vectors refer to motion, coordinates refer to location, and dimensions refer to orientation of an object. Okay, dimensions are not coordinates, and coordinates are not vectors. They're all different notions, different types of concepts. And you can never mix these, one with others. Okay, so here we have, just in case, I want to make sure you understood this as well. In math we have these so-called coordinates. They're not coordinates. They're known as number lines, and they have values. They have magnitude only, meridian, radius, and parallel. Okay. In physics, we have coordinates which are only qualitatively, and they have no numbers attached to them, and they're longitude, latitude, and altitude. Okay. So the coordinates of physics have nothing to do with the number lines of math that the mathematicians call coordinates. Okay. So yeah, they cannot use longitude, latitude, and altitude. And you can see another thing here, in that the arrows point towards the object. So when you're talking about coordinates in physics, you're talking about arrows pointing towards the object. How separated it is from this wall, that wall, and the third wall. That's all we're talking about. And yes, they are perpendicular to each other, whereas the ones in mathematical so-called physics, they bend them. They have curved number lines, curved dimensions, curved coordinates. Very scary stuff, They had to invent those as well. Okay, so here we have the number line of math. It has magnitude, but what does it have? It does not have direction. Okay, and you say, Bill, but you threw a bunch of numbers there. Is that doesn't look like a line? Where's the number line? Sorry, folks, I must have screwed up. So here, let's put the line in there. There you see the line. It's a squiggly line, and that's a number line. It's a squiggly one. It doesn't have direction, as you can see. So yeah, number lines do not have direction. What they have is just quantities, values, numbers, okay? Magnitudes is known, and physics is exactly the opposite. It says the dimension has direction and orthogonality, 90 degrees. You know, that's one of the features of dimensions. And what they don't have is magnitude. There is no magnitude with these things. Now you might say, hey, you put a 90 there. Is that a number? Well, I put a 90 there just to fool you. We call it perpendicular. Okay? Means one is perpendicular to the other. Okay? That's how we say it we put no numbers to perpendicularity, qualitative perpendicularity in physics. Okay, so let's make sure we understand that as well. Let me get rid of this one here. And here we have, again, we see that the squiggly line, you know, that's how time is. Time has no direction, it only has magnitude, values, right? Could be seconds, minutes, years, whatever. Time is a number line. Time is not a dimension, coordinate, or vector. It's a number line. That's all they have in physics, and it has no direction. It's perpendicular to nothing, so it doesn't have any orthogonality. Time belongs exclusively to math, has nothing to do with physics. Okay? We do not use the word time in physics. Why? Because time is a tool to describe, and in physics we explain. And until you understand the difference between an explanation and a description, you will not understand what I've just said. But that's for another day. Rainy day. Okay, so here we have the definition of time that you've always waited for all these 10,000 years. Here it is. We put it up for you. This is the definition of time, the scientific one, okay? We don't have any use for time, really, so in that sense, it's not scientific. We're just trying to define something in an objective, rational way so that the mathematicians can get an idea of what they've been using all these 10,000 years, which they've never been able to define. So here it is. Okay, time, a comparison of two motions. Okay, what you're comparing is two motions. There's an example: Earth orbit versus a free swinging pendulum. Okay, so what we do is we establish a relation between them. What is a concept? Concept is a word that invokes or embodies two objects. Okay, that's what a concept is. Let me repeat that. Concept, a word that invokes or embodies two objects. And here we have two objects. In this case, we're going to call the Earth one of the objects. It's got the moon and the sun there as well, but we're going to look at the Earth only. So we have one object, which is the Earth, and we have a pendulum, which is another. We're comparing. Okay, that's what a concept is, a comparison between two objects. And here we have it. We're saying, look, we have one object, which is the Earth, that's moving around the sun. It's called an orbit or revolution, whatever you want to call it. Orbital, maybe. And then you have the, the pendulum there. It's moving back and forth. And so we establish a relation between them, and we put some quantitative value and say, look, that's a minute, that's a second, that's a year, whatever. Okay? And so we establish these units, arbitrary units, based on things that can be used for technology or for everyday living. And that's what this relation is used for. That's it. It's no more mysterious than that. So yeah, time, comparison of two motions. Okay, that's all you're doing. Who can do the comparison? Does Mother Nature do comparisons? She does it. We do that, humans. We invented all concepts. We use all concepts. Mother Nature only uses objects, things. She moves things. She moves every atom from one place to another, from one second to the other, if you want to say it that way. One location to the other. That's how we say it. Okay, so because they never defined time, they ended up with all the mathematicians, right? They ended up with all these irrational. And yeah, that's the only way to put it. It's irrational. Well, all these irrational physical interpretations. Meaning no physical interpretation at all. If it's irrational, it's not a physical interpretation. You know, we can use angels, we can use spirits to say, okay, why did the curtain move? Well, because the angel moved it, or the spirit moved it. And what's a spirit? Well, I don't know, I've never seen one. Okay, so you're saying it happened by magic, and that's more or less where mathematical physics is. And here we have some magic from the establishment, the scientific establishment, the mathematical so-called physics establishment. And here's one of them. And it's about gravity warping time. And they say, new clock shows how gravity warps time. Science News, of course. PBS says, how does gravity warp the flow of time? And Wikipedia explains what they mean by that. It says the lower the gravitational potential, the closer the clock is to the source of gravitation, the slower time passes, speeding up as the gravitational potential increases, the clock moving away from the source of gravitation. And yeah, so they illustrate this nonsense, warp time, and they say gravity warps time. And yeah, the word warped belongs to physics, exclusively to physics. It doesn't belong to math. There's no number that you can say warped, okay? And time belongs exclusively to mathematics. Seconds, minutes, years, and so on, those belong exclusively to mathematics. We have no use for them in physics. And so the word warp belongs to physics, the word time belongs to math. And gravity cannot warp either one of them because gravity is a concept. You need to tell me what physical object warped the canvas in this case, I guess, right? And so, yeah, they have these irrational explanation that gravity warps time, and that's how they talk. Their language is totally irrational, and you do not use irrational language in science. People say, well, it's a figure of speech. You're not supposed to take it literally. No. These people take it literally because everything they publish out there for the public, which is where it's important, they use all these euphemisms, these figures of speech. And so people actually believe that, gravity warps time because the mathematician told me. Okay, so yeah, we have a problem because these people are conveying their irrationalities to the public, and the public knows no better, any more than people in the 4th century, they followed the priests, the only people who knew how to read in the town, in the village. And they said, well, he must know. He's the only one who knows how to read among us. He read the Bible, and he's telling us the angels came down and did this and that. And so this is more or less the situation today. People don't care about science. They only hear with half an ear. And they say, okay, they said there's a black hole. It says that gravity has warped time and warped light and all these other good things. And people just repeat that nonsense. It's an irrational language. If they don't mean it, tell us what you really mean. If you cannot put it into words, you're not a physicist. It means you don't know, you don't understand. That's why you can't put it into words. Your math cannot be translated into physics, okay? Or maybe the explanation you're giving is irrational and has nothing to do with the real world, even though your mathematical description does. That's another possibility. Okay, another irrational physical interpretation they've got out there is the twin paradox. We have this twin goes out there, for one of them there's been 30 years and for the other one has been 26 years because they went close, half the speed of light in this case, in this example. Okay, so we have this girl, she moves out with her rocket, goes out there half the speed of light, comes back, her sister is 30 years older and she's only 26 years older even though they're twins. Okay, this nonsense that they've built over the years, okay, is just absolute poppycock. And it's very simple to overthrow it. And that's, kid stuff. How many years have gone by? Well, we count the number of orbits of the Earth. That's how we measure the year. The word year is defined as orbits of the Earth around the sun. We don't count how many seconds the Earth went around the sun to give us the word year. No, it's one revolution of the Earth around the sun. That's what's called a year. And so whether the twin that left, went at the speed of light or half the speed of light, we don't care. When they come back, when this person comes back, right, we just have to count how many times the Earth went around the sun. And we don't care about their atomic clock that was on board or the one that they left on Earth. We don't care about that. These people want to count your birthday years, with seconds. And they say, I want so many, one candle for every second of my life. And so how old are you? Well, I don't know. Let me calculate that. How many seconds are there in a year? And then was the Earth moving at the speed of light? And were we close to a black hole? So they get into all these idiotic situations when it's very, very simple. The Earth went around the sun 20 times, 30 times, 40 times. When the person who went out and came back, speed of light, half the speed of light, 95% of the speed of light, we don't care. When they come back, we just count the number of revolutions of the Earth around the sun. We'll know how old both of them are, how both of them aged, okay? How much they both aged. Okay, here we have another irrationality, and this is by a superhero of the establishment, okay? We have good old Brian Greene. He's going to jump into what is called a wormhole. He's going to fall into yesterday or this morning, I think. And he meets himself. They call this science. They refer to this as science. They say it's time travel. He traveled to the past. He saw himself in the morning. Okay? He shakes hands with himself. Is this science, folks? Or is this absolute poppycock coming out of Harvard and Cambridge? Cambridge. Right? Yeah, the Cambridge folks and the Harvard folks, they believe in this nonsense. They're a bunch of idiots. Oh, sorry, did I say idiots? I meant to say stupid idiots. Okay? They got to be mentally retarded to believe in this garbage. This is not science. This is not nothing. For them to show this to the public in the guise of science, it's offensive. That's what it is. It's offensive. Okay, so that's another irrationality. Can you go to the past? Can you visit Napoleon? You know, Napoleon was at Waterloo. Julius Caesar, he went to England and beat up whoever was living there at the time, brought his Romans over, right? Can we do that? Can we go see Julius Caesar? Can you go see Alexander the Great? Shake hands with him. Well, here's the problem, okay? Let's look at the problem from a physical point of view, why that's totally irrational, okay? And here it is, okay? Here we have the frames of the Universal movie. Universal movie, you know, is one frame. Every atom in the universe is in that frame, and it has only location. In the next frame, all of them, all atoms in the universe have a different location, and so on down the line, right? And so why don't we look at two of these frames, okay? Let's look at number 156 and number 906, okay? We've got two frames at random, obviously, right? Okay, so we have these two frames, and what we're going to do, let's call frame 906 the present. Okay, let's call that one the present. That's the last frame. It hasn't moved yet, right? And what we're going to do, we're going to try to move from frame 906 to frame 156. Okay, so we're going to move in that direction, okay? We got that so far? Very easy. Okay, so this is what we call time travel, right? They say we can go to the past. What's the problem with this explanation, this physical interpretation of the mathematical physicists? Well, the problem here is that means that both frames exist simultaneously. Okay, so in one frame 156, you have every atom in the universe. And in frame 906, you have the same exact number of units, number of atoms in the universe. They're just at a different location. But in order for you to jump from frame 906 to 156, all those atoms have to exist twice. They have to be currently in 156 as well as 906. That means that in 156, let's say you went to visit your mother who already died, right? But in frame 156, she's still alive, right? That was when she was still living. And you just left your brother, your father, whoever in frame 906. He's still living. You haven't killed him because you traveled, right? So if frame 906 exists with every atom in the universe, including your brother, and 156 exists because you were able to visit your mother when she was still alive, that means every atom in the universe was also in frame 156. Then we have all these atoms existing twice. And what we're doing really when we say this is that for every location in the universe, there really is no motion. What you're doing is creating the atoms all over again. You're saying that at 155, you had all these atoms in the universe, and at 156, you didn't move the atom. What you did is create every single atom in the universe at a new location. That's what you're saying. That's why it's idiocy what comes out of Harvard and Cambridge when they talk about time travel, time traveling to the past or traveling to the future. What they're saying is that you're creating new atoms for every location in the universe. Okay, that's what they're saying. That's why this is more than irrationality. It's offensive for these people who studied 10 years and more, to say this idiocy and give this to the public. Okay, that's put into right context. We call it idiocy. Okay, we call it irrationality, and we spit on these people. Okay, there's no love lost with them. Okay, so here we have another irrational from good old Brian, and he's going to cut the space-time, the loaf of bread. He's going to cut it into slices of time. Okay, and so he says this is where the universe starts. That was the Big Bang right there, and the present is on your right. Okay, and we have all these time slices. And again, these time slices are every atom in the universe is in each one of those slices. So he's saying, yeah, exactly that. All these slices exist simultaneously. And what we're doing is creating new slices for every, for every piece of the bread. And what we have is this. Here we have, the two slices are there. The one somewhere in the middle and the one close to the end. Okay, we have those two slices are still there. You're creating every atom in the universe again and again. Instead of moving, there is no motion. What you're really having is you're creating the same atoms at a new location. That's what you're doing. And you're not destroying anything. All atoms are still there. Okay, then yes, you could conceivably, if you could travel in time, all you have to do is go to the right slice, right? And meet Galileo, Newton, whoever you want to meet. You would go to that slice that's in Mother Nature's cabinet, the filing cabinet, and there it is. You end up in all those atoms of the universe that were there at that moment in time. Does that make any sense? No, it doesn't. And that's why this special relativity is just special poppycock. That's all it is. Nonsense. It's poppycock. Idiocy. Okay? It doesn't belong in science for sure. And why it's fed to the public is something you have to ponder. Okay? Okay, so let's get on to spaghettification. What does all this have to do with spaghettification? Well, it's just another irrationality, just like the ones you just heard. Okay? There's no difference between them. Here's the spaghetti side. Okay? In order to understand it, we need to understand what a black hole is. And here we have a definition that came out very recently in an article. And it says, what is a black hole? It says, every star we can see, including our sun, exists in a careful balance. The immense weight of the star's outer layers presses inwards. Okay, we're going to crunch this star, right? It's going to compress itself through gravity, while the pressure resulting from fusing elements together in the star's core pushes outward. So we have a pull inwards and a push outwards, right? The people inside the fort, they're defending themselves against the Indians who are attacking them, essentially. When the star's core can no longer produce enough fusion energy, the balance is disrupted and the star dies. In other words, the Indians on the outside are able to overcome the defenders on the inside of the fort. That's essentially it. Exactly how the star dies depends on how massive it is. Smaller stars like our sun simply cast off their outer layers, leaving behind their core as a white dwarf. Okay? More massive stars die in a much more dramatic way, producing a brilliant supernova as their outer layers crush the core. In some cases, the core can only be crushed down so far. This leaves behind a 10-kilometer wide remnant at the center of the explosion, known as a neutron star. For the most massive stars, though, nothing can prevent the complete collapse of their core. It gets crushed down to what? What astrophysicists call a singularity. What is a singularity? Well, it's a no volume, no size, no shape, nothing. It's got no matter because it crushed it all out of existence, meaning it's got no mass. So again, we're talking about absolutely nothing. And instead of calling it nothing and zero volume and zero shape, etc., they say an infinitesimally small point. No, that's not what it is, because Mr. Chandrasekhar proved mathematically that it goes down to zip, not to a point, not to infinitesimally small, but to absolute zip, nothing. that still contains all the mass of the original core. It cannot, because all matter is crushed out of existence at the singularity, so it cannot have any mass, because mass is a measure of the quantity of matter. So we have no matter, it's crushed completely out of existence, but we have mass. You got rid of the elephant, but the weight of the elephant remains behind. Yeah, sure. Yeah. In math, maybe. Okay. So here we have it. Okay, we have, this is what they're explaining. They're saying here you have the star. It's going to collapse. Okay, give me a second here. And it's going to crush itself, squeeze itself. And it goes right out of existence, and an explosion, leaving behind a little ball that eventually also shrinks to absolutely nothing. Okay, how's that for effects, mathematical effects? Does this have anything to do with physics? Well, some of it does, some of it doesn't, especially the black hole part. Okay, if it collapses down to 0D, we no longer have physics, because physics principle, the golden principle of physics is you can't do physics without an object. And what they're saying, they're going to do physics without an object. They're going to have a singularity, and they're going to move the singularity at the speed of light. They're going to do all kinds of things with the singularity. They're going to have the singularity affect stars in the vicinity, move them around, suck off their gases, fly them alive. They're going to do all these fancy things to stars in the vicinity, or matter in the vicinity, gases and so on, atoms. But what is doing it? Well, it's a singularity. That's what's doing it. That's the cause. That's the motor that gets all this thing rolling. And you cannot do it with a singularity, because a singularity is zero-dimensional, no size, no shape, no matter, meaning no mass, no volume, no nothing. That's a definition of nothing. That's what a singularity is. Okay? And what they say, the way they get around that, they say, well, what happens at the singularity, the laws of physics break down. We don't know what happens there. And then that's how they came up with Big Bang as well. Big Bang is, we don't know what a singularity is or where it came from. Maybe God, with his magic wand. But once you have it, then you can do all kinds of miracles. You need that singularity to start the universe, right? Okay, so here we have Spaghettification. It says, point of no return. Another article. It says, observatory detected X-rays coming from Cygnus X1. Cygnus the swan, right? Which we now know is a black hole. They know this, okay? In orbit around a regular star in our own Milky Way galaxy. While scientists have dramatically improved our understanding of black holes since the first detection, these objects remain quite mysterious. Yeah, they will forever, as long as you don't define your terms or tell us what you're talking about. This is because light can't escape from a black hole, so they cannot be observed directly with telescopes. So they think that observation gives them insight, okay? And without observation, I guess they're ignorant, and they can't see inside a black hole, so they're ignorant of black holes. Yeah, that does make sense. Instead, astronomers primarily look for the ways that black holes influence and distort matter around them. In other words, they're going to prove the black hole indirectly. They look at the visible stuff and they say, oh, it was caused by a black hole, meaning by mass, meaning by, unseen elephant that left his weight behind. That's more or less what they're saying. When an object gets too close to a black hole, right, it will start to experience tidal forces. These tidal forces which are going to spaghettify you, okay? Tidal forces refer to the distortion of one object by another due to the difference in the gravitational pull on the near and far side of an object. In other words, it's going to stretch you. And what they're going to be referring to essentially is the fact that if something falls into a black hole, especially like an astronaut, hopefully feet first, could be head first, right? The astronaut's got to be stretched. And that's what they're saying. Because you have all these tidal forces that are somehow touching you. What are these tidal forces? I mean, what's in the black hole? Is it sand? Is it ether? Are there warped number lines? What is stretching? What's coming in physical contact with the astronaut? That's what we want to understand. And they say it's just tidal forces. Oh, okay. Whatever those are. Okay, so here we have the process. Again, it says spaghettification. they're going to simulate by throwing a camera inside, through the event horizon. He says the camera starts off with 640 million kilometers away, or a little over 4 times farther than the Earth is from the sun. This simulation depicts a one-way trip, okay, though, because the camera eventually encounters a boundary around the black hole known as the event horizon, okay? Once the boundary is crossed, you're going to go cross the event horizon, right? Even light, the fastest thing in the universe, doesn't have enough speed to escape. Okay, so there's a tie game. I guess the fastest the black hole or the event horizon pulls towards the singularity is the same speed that light has to try and escape. Okay, and that comes from Einstein saying that nothing travels faster than the speed of light. Okay, how it pulls the light, the little photon, we don't know. We don't know what came in contact with a photon. It's just done because nothing can go faster than light. That's the way they say it. It's a force. Whatever force is, what physical object touched a photon? That's what we want to understand, and that's the part they'll never tell you. Once the camera crosses the horizon, its destruction by spaghettification is just 12.8 seconds away. Okay, so at least you got 12 seconds to breathe, right? Spaghettification is the scientific term. I like that. It's a scientific term for what happens to something or someone that gets too close to the center of a black hole. The intensity of its gravitational pull increases so quickly as you approach that you would feel it far stronger in your feet than in your head. So they're going to stretch you out, like they did in the old days when you didn't believe in God. Well, they would stretch you a little bit, put you on the rack. That's more or less what they're doing here. The closer you got, the more you would become stretched by these tidal forces like spaghetti. Okay, so now you know where the scientific term comes from. It comes from spaghetti. These noodles. Okay, here's the trip. This, if you want to visualize it, here it is. Okay, the guy falls into a black hole, loses his head, which comes later, right? And that's how he falls in there. Going into the black hole. Don't ever fall into a black hole. Okay, he falls in there. And so what's the issue? Well, one of the issues here is given to us by this lady, and I talked about her last time. Her name is Jana Levin, and she's going to tell you that the singularity, it doesn't exist. After all that's done, after all is said and done, she said, well, by the way, it doesn't exist. Okay, here it is. Hear it from the horse's mouth. Okay. Listen carefully, here it goes.
Once you pass the event horizon, space becomes time and time becomes space. So from the outside, if you're an astronaut, you're watching your friend, another astronaut, going into the black hole, it's as though your times become rotated relative to each other. So the profound thing is, as an astronaut on the outside, looking at this round event horizon, you think of the center of black hole as a point in space. But to the person who's fallen in, it's not a point in space at all. It's a point in time. The singularity, or the end of it all, the crush in the center of the black hole, is in their future. So they can no more avoid the singularity than you can avoid the next instant of time coming. So the death in the singularity is inevitable, although we don't really think the singularity necessarily exists.
Although we don't really think the singularity necessarily exists. Although we don't really think the singularity necessarily exists.
That singularity probably doesn't ever actually form.
That singularity probably doesn't ever actually form. That singularity probably doesn't ever actually form.
Okay, so the singularity never forms and it doesn't exist. That's great. That's a great way to finish your dissertation. You tell them all about what happens with you falling into a singularity, and then at the end, by the way, it doesn't exist. So what was the talk about? What was the spaghettification about if the singularity doesn't exist? Okay, so we have a problem, and Here's one fellow who tells us something even more scary. It says that nothing really disappears in a black hole. Everything is there because, like Jana said, right? You fall forever towards your future, but the future is always in the future. So you never reach the future because it's always in the future, okay? So singularity is always in the future. You're falling forever, meaning that between the event horizon and singularity, all the garbage that ever fell into a black hole is still there. It doesn't get crushed out of existence. Every atom is not wiped out. It's still falling. It's falling forever. That's what they're saying. Now you say, well, how come we can't see it? Yeah, because they're saying they can't, whatever's inside cannot send you a photon to your eyes, you the observer outside. So you're on the outside trying to see in, you don't know what's going on because you can't see beyond the event horizon, no light can come through there. But everything that fell in is still in there. It's still alive. If it's a cat or whatever, it's still alive in there, right? And unless it's Schrodinger's cat, right? Could be dead or alive. But it's still in there. It hasn't been crushed out of existence. That's what these people say. So we have a contradiction because you have some who say it's crushed out of existence and others say that it's not. It's still there between the event horizon and the singularity, meaning everything is being stretched from one end to the other and forever stretch. What a terrible way to die, you know. You're being stretched forever because your feet never reach the singularity. It's always in the future. And here you have this fellow, so listen to him carefully. He'll tell you in a very scientific way. Here it goes, okay? Listen.
What happens to you depends on the type of black hole. First, we have classical black holes. These are black holes that exist forever. If you fall into this black hole, it would take an incredibly long time to reach the center. The center would keep getting closer and closer, but you would need an almost infinite amount of time to reach it. So it would feel like your journey would never end.
You would need an almost infinite amount of time to reach it. So it would feel like your journey would never end.
An infinite amount of time to reach the singularity, your journey will never end. You're still stuck falling through the black hole. So everything that ever fell into a black hole is still until the end of time, or the crunch, the big crunch, whichever comes first. Until that time, everything will still be inside the black hole. And so why is this a problem? Well, let me tell you here. Here's a space-time diagram again. Okay, we have time and space, right? And let's switch them around because it really doesn't matter, but it's probably easier to do it this way, space, time, right? And they say you can switch one coordinate, what as they call them, one with the other, so it wouldn't matter. We can switch them around. What these idiots, I'm sorry, did I say idiot? I meant stupid idiots. These irrational, stupid idiots. What they're saying is that the astronaut's head's on Monday, but his feet are on Thursday. Okay, so he's being stretched completely out there, poor fellow, on the rack. They used to stretch him for not believing in God. These guys get stretched for believing in Einstein, I guess, And so here you have it. Yeah, the astronaut is being stretched as his feet approach the center of the black hole, the singularity. And so that's essentially how this guy's going to die. But the interesting part about this is that you have some people who say, hey, you can even survive the trip and end up in another universe. And so here we have first the group who says that all matter is crushed out of existence. They have no doubt about this. Here you have these people, these testimonies. One is from the University of Maryland. The matter that forms a black hole is crushed out of existence. I don't know what he means by that, but when I hear crushed out of existence, it exists no more, right? Just as the Cheshire cat disappeared and left only a smile behind. Black hole represents matter that leaves only its gravity behind. So there's no more matter, but all the mass is behind. That's what these people are saying. Here's another fellow, University of Texas. The singularity, where everything, including space and time, are crushed out of existence. Here's another one, David Harrison. If the mass of the star is greater than about 3 solar masses, it goes through the neutron star stage and keeps collapsing. In this case, the gravitational attraction is so intense, the neutrons are literally, what? Crushed out of existence. We call the object a black hole. All the mass, light, and energy that has ever fallen into a black hole is compressed by its own overwhelming gravity into a point that is infinitely small and infinitely dense. Space has been, what? Squelched out of existence. So how can there be anything there? How can everything be compressed into a point if the point itself is zero-dimensional, zero volume, zero shape? And time has been squeezed to a stop. Time has been squeezed to a stop. I absolutely love that one. And here's a final one. Time magazine. Whole stars can vanish from sight within black holes. Literally, what? Crushed out of existence. So yeah, matter does get crushed out of existence in the singularity. There's nothing there. And they call this non-entity. They call it a singularity. And they say this non-entity, no matter, meaning no mass, moves stars, gases, atoms, rockets, astronauts all around like you can believe. How they do it, we don't know, because we have no idea what the mechanism is. They just say it does it through mass. Okay, here we have good old Derek, and he tells us in his famous words. He says, Derek Muller, imagine you trap your nemesis in a rocket ship and blast him off towards a black hole. Gravity gets stronger as you would expect him to speed up. But that is not what you see. Instead, the rocket ship appears to be slowing down. That's because from your perspective, his time is slowing down at the very instant when he should cross the event horizon, the point beyond which not even light can escape. He and his rocket ship do not disappear. So what happens? Instead, they seem to stop frozen in time. The light from the spaceship gets dimmer and redder until it completely fades from view. This is how any object would look crossing the event horizon. Light is still coming from the point where he crossed. It's just too redshifted to see. So the object is there. It's that you can't see it, right? That's all he's saying. The light is not reaching your eyes. But if you could see that light, you would see everything that has fallen into the black hole frozen on its horizon, including the star that formed it. So the objects are not crushed out of existence according to this fellow. So we have all these contradictions. Some people say it's crushed out of existence, goes to the singularity. Other people say you're stretched forever. You never reach the black hole because it's the singularity is just a point in time, not a thing. And then this guy says, yeah, everything's on the event horizon. If you had the eyes, you could see it there. It's just frozen in time, so to speak. And Derek, because of that, because he's got these irrational notions, says that you can even survive the spaghettification process. And I don't know how he does that, but this is what he says. Okay, I'm just listening to him. You're now inside the inner event horizon. You're not doomed to the singularity. Here you can actually see the singularity, a point. It's thought that you can actually fly through the singularity. You're going to fly through it, this little point that has no volume. You're going to go through a no volume. You could find yourself in a white hole, which would push you out into a what? Whole other universe. You're going to come out of another universe through a zero-dimensional hole. Hole, zero-dimensional, I don't know if Bugs Bunny can creep through one of those. It says that little point there where they cross the singularity, that is an Einstein-Rosen bridge. It's a bridge that is long. It connects the space of both universes. If you go beyond it, you end up in the parallel universe. So that is how we could use a black hole to travel from one universe to another. Now, isn't that all scientific? So scientific that makes me want to puke. What are these people talking about? These people don't belong in science. They're not scientists. They're comedians. They're in the entertainment business. They make money by giving you the false impression that you're receiving your shot of science for the week. So they say, oh, watch me on Friday or whatever. And the person goes there, watches, and oh, that was so great. I can travel through a wormhole to another universe. I think these people are trying to escape the reality here on Earth. That's what they're doing with all this nonsense. Now you might say, well, that's good. Well, yeah, I don't know. It'd be nice, a little more reality instead of all this poppycock. But this is what these people are into. They're all studying black holes, dark matter, dark energy, Big Bang, all kinds of nonsense that they study out there. All the papers written today are on these subjects. Everybody's heavily into that. And this is what these people are coming out and just passing out to the next generation of idiots who study at Cambridge and Harvard. And this is what they come out. Bunch of math, irrational explanations. With that, I'll see you next Sunday. Bye-bye.